Earlier versions of Solidity allowed the use of local variables even before they were declared. These variables could be declared later or they could have been declared in another scope. And this led to undefined behavior, as you may expect. Solidity version 0.5.0 and beyond changed this to implement the popular C99 style scoping rules, where variables can only be used after they have been declared and only in the same or nested scopes. Certain operations in Solidity are considered costly or expensive in terms of the amount of gas units they use. And if such operations are used inside loops, they end up consuming a lot of gas, which could result in unexpected behavior. The best example of a costly operation in Solidity is that of state variable updates. Recall that in Solidity, state variables are stored in the storage area of the EVM. Updates to such state variables use the store instructions of the EVM, which are one of the most expensive EVM instructions. As of the latest upgrade from Berlin, stores cost 20,000 gas units if they are a cold store where the state variable is being updated for the first time in the context of this transaction, or they cost 5,000 gas units if it is a warm store, in which case this variable has already been updated in the context of this transaction. So either 5,000 or 20,000 gas units are consumed every time a state variable is updated. So as you can imagine, if such updates are done inside loops, then they could end up consuming a lot of gas and result in an out of gas error if the amount of gas supplied in this transaction is less than what is required. The solution here is to use local variables instead of state variables as much as possible. And the reason is because local variables, if you recall, are allocated in memory, and memory updates using mstores only cost 3 gas units compared to the 5,000 or 20,000 that storage updates cost. So this notion of costly operations being used inside the loops leading to out of gas errors, and in the worst case leading to a denial of service, can be mitigated by caching and using local variables as much as possible instead of storage variables. Similar to state variable updates, external calls inside loops should also be used very carefully. And the reason is external calls cost 2600 gas as of the latest upgrade. This is more of a concern if the index of the loop is controlled by the user, because in that case the number of iterations of the loop is also user controlled, because that could result in a denial of service if one of the calls inside the loops reverts, or if the execution runs out of gas because the gas supplied in the transaction wasn't enough. So the mitigation here is to avoid or reduce the number of external calls made inside loops, and also check that the loop index cannot be user controlled, or that it is bounded to a small number of iterations. And this again is in the context of preventing opportunities for denial of service. Costly operations such as state variable updates and external calls, especially made inside loops, are also relevant in the context of the block gas limit. Recall that Ethereum blocks have a notion of a block gas limit, which limits the total amount of gas units consumed by all the transactions included in the block to a maximum upper bound. And this upper bound until recently was 15 million gas units. And this has changed significantly in how it works because of EIP 1559, but the notion of a block gas limit still remains. And the reason why this is relevant is because if expensive operations are used inside loops where the loop index may be user controlled, then such expensive operations may result in an out of gas error. And this out of gas could not only come from the amount of gas units supplied in the transaction that resulted in all this execution, but it could also arise because of the gas consumed by this transaction exceeding the gas limit for this block. So the mitigation here is again to evaluate the loops and make sure that a lot of these expensive operations are not used inside the loops, and also to check if the loop index is user controlled and if it can be bounded to a small finite number so that opportunities for denial of service are prevented. Events should be emitted within smart contracts for all critical operations. Emission of events that are missing for such critical operations is a security concern, and the reason for this is because it affects off-chain monitoring. Recall that events emitted from smart contracts end up storing the parameters of such events in the log part of the blockchain, and these logs, either the topics part or the data part, can be queried by off-chain monitoring tools or off-chain interfaces to understand what is happening in the smart contracts. And this is an easier way to understand the state of the smart contracts without having to query the contracts themselves. These events become very important from a transparency and user experience perspective. And so the best practice is to recommend the addition of events in all places within the smart contracts where critical operations are happening. And these could be updates to critical parameters from the smart contract application's perspective. These could be operations that are being done only by the owner or privileged roles within the smart contract. So in all such cases, events should be emitted to allow transparency and a better user experience. Having talked about events, let's now focus on the event parameters. Event parameters not being indexed may be a concern in certain situations. Recall that event parameters may be considered as either indexed or not, depending on the use of the index keyword, and this results in those parameters being stored in the topics part of the log or the data part of the log. And being stored in the topics part of the log allows for those parameters to be accessed or queried faster because of the use of the Bloom filter. And if they're stored in the data part, then it results in a much slower access. There are certain parameters for certain events that are required to be indexed as per specifications. ERC20 token standard, for example, has transfer and approval events that require some of their parameters to be indexed. And not doing so will result in the off-chain tools that are looking for such indexed events to be confused or thrown off track. So the best practice here is to add the indexed keyword to critical parameters in an event, especially if the specification requires them to be indexed. This comes at cost of some additional gas usage, but allows for faster querying. The concern here was that of incorrect event signature in libraries. And the reason for this happening was because if events used in libraries had parameters of contract types, then because of a compiler bug, the actual contract name was used to generate the signature hash instead of using their address type. And this resulted in a wrong hash for such events being used in the logs. And the mitigation here was to fix the compiler bug, which happened in version 0.5.8, where the address type was used instead of using the contract name incorrectly. Unary expressions are where an operator is used on a single operand as opposed to two operands, in which case it would be a binary expression. And such unary expressions are susceptible to typographical errors by developers. For example, let's take a look at this scenario here where there's a variable x and the developer wants to increment it by 1. So the way to do that is to say x plus equal to 1, which effectively is x equal to x plus 1. But if the developer interchanges the order of plus and equal to and instead uses x equal to plus 1, then this would result in reinitializing the value of x to plus 1. And the reason for this is plus 1 is a unary expression whose value is 1, and x would get initialized to that value. As you can imagine, such typographical errors are likely to be made by developers. It's very easy to make these, switching the order, and if they are considered as valid by the compiler, then it's very hard to notice such errors both by the developer as well as by the security auditor. So in order to prevent some of the most common usages that result in such typographical errors, the Unary Plus was deprecated as of Solidity compiler version 0.5.0. Zero address in Ethereum and Solidity has a special consideration. Recall that Ethereum addresses are 20 bytes in length, and if all these bytes are zeros, then it's referred to as a zero address. These zero addresses become significant because state variables or local variables of address types have a default value of 0 in Solidity. And these zero addresses are also used as burn addresses because the private key corresponding to this zero address is not known. So any ether or tokens that are sent to the zero address gets burnt or inaccessible forever. And if addresses used for access control within the smart contracts end up being zero addresses, such functions cannot be invoked, again because of the lack of knowledge of the private key. So such functions cannot be called, which might in the worst case end up in such contracts getting locked. So the best practice is to perform input validation on all address parameters that are of address type to check that they are not zero addresses. This is a very commonly encountered security pitfall where address parameters of constructors, setters, or public external functions are not input validated to not be zero addresses. In the best case, such scenarios only result in exceptional behavior at runtime, but in the worst case, they could result in tokens getting burnt or the contract being locked. Another security pitfall related to addresses is the aspect of changing values of critical addresses. Certain addresses within the context of the smart contract may be considered as critical. These may be special privileged roles such as the owner address, which has special access to certain functions for updating critical parameters or doing other administrative aspects related to the smart contract. Or these could also be addresses of other smart contracts that are used within the context of the application. And as you can imagine, there may be scenarios where such addresses would need to be changed. So for example, the default owner of a contract could be the deployer of the contract, and we may want to change this to another address later on. Or if the addresses correspond to other smart contracts, then we may want to change the value to another smart contract once we have updated it. In such scenarios, the security pitfall is when this change is done in a single step. And this may be using the ownable library from OpenZeppelin, where there is a transfer ownership function provided that transfers the ownership from the existing owner to a new owner that is provided as a parameter. And this happens in a single step where the owner variable is updated to the new address provided. This single step change is prone to errors, because if an incorrect address is used as the new address, then it may result in that contract getting locked forever. And the reason for this is the address used may be an address for which we do not have the private key. So we cannot sign any transactions from that address, which results in all the administrative functions or any of the address change functions being inaccessible thereafter. The mitigation here, or the best practice, is to move away from a single step change and to move to what is known as a two-step change, where the first step grants or approves a new address as being the owner or as being that changed address. And the second step is a transaction from the new address that claims itself as being the new owner or as being the new address. So this two-step change allows any errors that happen in the first step, where we grant or approve it to an incorrect address for which we do not have the key. It allows us to recover from this mistake, because the second transaction, which claims itself as a new address, can never be done if an incorrect address was used in the first step. So this aspect of critical addresses being changed and allowing errors to be recovered by moving away from a single step to a two-step change is a critical aspect of mitigating the risk from incorrect address changes. This security best practice is related to the use of asserts within smart contracts. Assert should be used only to check or verify program invariants within the smart contracts. They should not be used to make any state changes within the predicates, and they should also not be used to validate any user inputs. And the reason for this is because if any state changes are made as a side effects of the predicates within asserts, then those could be missed both by developers during maintenance or when they are trying to do any testing, and they could also be missed by auditors because these state changes are not expected to happen within asserts. And similarly, asserts should not be used to validate user inputs, because that should be done using require statements, which we'll see in the next slide. As a general rule, we do not expect to see any failures from asserts during normal contract functioning, and therefore these best practices become very relevant. This best practice is related to the use of asserts versus require and the specific conditions in which they should be done. These two aspects are related, but they have different usages. Asserts, like we just mentioned, should be used to check or verify invariants, where these invariants are expected to be held during normal contract functioning. So we do not expect any of these asserts to fail during the contract execution. And any failures are really critical panic errors that need to be caught and dealt with in a very serious manner. On the other hand, require is meant to be used for input validation of arguments that are supplied by users to various public or external functions, where we do expect failures to happen because the user provided values may be zero addresses in some cases, or maybe values that are out of range or do not make sense from the smart contracts perspective. So this difference is something to be kept in mind, and the best practice is to use assert or require appropriately as the situation demands. This had a more significant impact until Solidity Compiler version 0.8.0, because until then, require used the revert opcode, which refunded the remaining gas on failure, whereas assert used the invalid opcode, which consumed all the supplied gas. So until that version, the usage of assert or require incorrectly would result in different gas semantics, because in one situation the remaining gas would be refunded, whereas in the other case all of it would be consumed. So this affected user experience as well. But this has changed since version 0.8.0, where both require and assert use the revert opcode and refund all the remaining gas on failures. This security best practice is related to the use of deprecated keywords in Solidity. Over the different compiler versions, different keywords have been deprecated to favor one over the other. So for example, message gas has been deprecated to favor gas left, throw has been deprecated to favor the use of revert, SHA-3 for catchat256, call code for delegate call, constant keyword for view, and var keyword for using the actual type name instead. So all such deprecated keywords may start initially as compiler warnings, where the compiler warns us not to use these keywords, and over the future versions these warnings could be converted into compiler errors, in which case the compilation fails. So the best practice here is to simply avoid the use of deprecated keywords even if they are compiler warnings, because these warnings can become errors in the future compiler versions. Recall that functions in Solidity have the notion of visibility, where they could be either public, external, internal, or private, and this affects which users can call these functions. So public and external functions are callable by anyone, depending on the access control that is enforced additionally on top of that, whereas internal and private can be called only from within the contracts or the derived contracts. Until Solidity version 0.5.0, this visibility specifier was optional and it defaulted to public. And this aspect led to vulnerabilities where the developer forgot to mention or specify the visibility, in which case it became public by default and resulted in malicious users being able to call these functions and make unauthorized state changes completely unexpected by the developer or the smart contract. So this optional specification of function visibility defaulting to public visibility was removed as of Solidity version 0.5.0. So this was a big change when it came to increasing the security of smart contracts. And since that version, function visibility is required to be specified explicitly for every function. Contracts that inherit from multiple contracts should be careful about the inheritance order, because if more than one such base contract defines an identical function, then the particular function implementation that gets included in the derived contract depends on this inheritance order. And the best practice is for this inheritance order to be from the more general implementation to the more specific implementation. Another security pitfall related to inheritance is that of missing inheritance, where a particular contract within an application might appear to inherit from another interface in that project or another abstract contract without actually doing so. And it might appear so because of the contract name that is similar to the abstract contract or the interface name, or also because of the functions that are defined within this contract, their names, the parameter types, and so on. And this appearance might give the notion that it is inheriting without actually inheriting. This affects not only the readability and maintainability aspects for the developers or the project team, but it also affects the auditability, because the security reviewer might look at this contract and assume certain aspects, thinking that it's inheriting from the similarly named interface or abstract contract, whereas in fact it does not do so. So the best practice here is to make sure that the inheritance is done appropriately And if there are similarly named contracts where they do not actually inherit from each other, then the name should be changed. But if they do, in fact, are meant to be inherited, then specifying that inheritance will help. Gas griefing is a security concept that becomes interesting in the context of transaction relayers. Recall that on Ethereum, users can submit transactions to the smart contracts on the blockchain, or alternatively, they can submit what are known as meta transactions, which are sent to the transaction relayers where they do not need to be paid for gas, and the relayers in turn forward such transactions to the blockchain with the appropriate amount of gas. And in this scenario, the users typically compensate the relayers for the gas out of band. In such situations, it becomes necessary for the users to trust the transaction relayers to submit those transactions or forward their transactions with a sufficient amount of gas so that their transactions do not fail. Recall that Solidity has value types and reference types. This security pitfall is related to the use of reference types in function parameters. When structs, arrays, or mappings, which are the reference types, are passed as arguments to a function, they may be passed by value or they may be passed by reference. And this difference is dictated by the use of either the memory or the storage keyword that specifies their data location. This was optional before Solidity version 0.5.0, but since that version, it is required to be specified explicitly. This difference is critical from a security perspective because pass by value, if you recall, makes a copy. So any changes to the copy does not affect the original value, but pass by reference creates a pointer to the original variable. So any changes to the passed value is actually modifying the original variable itself. This, if not treated properly, could lead to unexpected changes and modifications of the original variable or a copy, which could have very different behavior and impact for the smart contract logic. Arbitrary jumps are possible within Solidity. Solidity supports many different types, one of which is a function type. These function type variables are not frequently encountered, but if they are indeed used, especially within assembly code, in making arbitrary manipulations to variables of these types, then they could be used to change the control flow to switch to an arbitrary location in the code. This is something to be paid attention to, and from a development perspective, something to be avoided. Assembly in general is very tricky to use, and it bypasses many security aspects of Solidity, such as type safety. So it's best to avoid the use of assembly if possible, and definitely to avoid the use of function type variables and making arbitrary changes to it, because that could result in changes to control flow that is unexpected by the developers or the smart contract auditors. Hash collisions are possible in certain scenarios where the ABI encode pat primitive is used with multiple variable length arguments. And this happens because this primitive does not zero pad the arguments, and it also does not save any length information for those arguments, as a result of which it allows packing. And this packed encoding could lead to collisions in certain scenarios, which you can imagine can affect the security of the smart contract. The best practice here is to avoid the use of the packed primitive where possible and use the encode primitive instead. And in scenarios where it cannot be avoided, one should at least make sure that only one variable length argument is used in this primitive. And certainly users who can reach this primitive via function calls should not be allowed to write to the parameters used and taint it to force collisions from happening.